Okay, let's begin. So, in the last class, we were trying to increase the gain of the opamp, right? And we did that by how did we do that? We are trying to do a cascode, and of course, you guys must be familiar with the cascode at this stage. So, if I draw for the NMOS, so we'll have an NMOS current source and then a current buffer like this, right? And if I call this M2 and M4, I think now you know what is the output impedance. So this is basically GM4 or not roughly, right? So now let me ask this. So if let us say the drain voltage here changes by delta V, how much do you think this drain voltage will change by? Or first of all, I'm changing delta V. So do you think here the change will be, let's say call it delta V, I know delta V naught or something. Do you think delta V naught will be greater than delta V or less than delta V or equal to delta V?
Less than.
Yeah, why? Sorry? It is not a voltage buffer, right? It is a current buffer. I mean, okay, see, voltage buffer is when you apply the input at the gate and take it from the source. But here, the voltage is applied at the drain, right? I mean, most of you see, huh?
I'm guessing current should be constant, the VGS should be.
Okay, why is the current constant? I mean, let us say you, at operating point, this is drain voltage is some voltage, gate is at some.
Not constant, but okay, if it increases, it will be square dependence on VGS. So it will get under root and then.
Not really, I mean.
I just guess.
Okay, first of all, what is the. I mean, is everyone. So if I just had this M2. Right, this also is a decent current source, right? But it is not an ideal current source, right? Why is that so? What prevents it from output resistance, right? In other words, basically the current here also has dependence on the drain to source voltage, right? If you have an ideal current source, irrespective of the voltage across its terminals, the current is constant. Here it is no longer the case, right? So, everyone is confident that if I have a current buffer like this entire guy will be a better current source compared to this. Okay. So, basically, these are the same terminals now, right? This is our old current source. Right side is the new current source. Okay. So, this is a bad one, this is a good one. So if I increase the voltage across this current source, you will expect that the current here will change a lot. Whereas here, at least we know that this is a better current source. The current should not change a lot. So which means this VDS should also not change a lot because this is what sets the current. The bottom transistor is the main current source. What you have at the top is just a current buffer. Is that fine? And everyone is fine that this cascode is a better current source. So which means if I change the voltage across this current source, even the change in the current will be small. So which means the change in the drain to source voltage of the main current source I have here must also be much smaller. And qualitatively, can you tell me what will this change be? Delta V naught. So this is true. It's going to be less than that. Okay, why don't you guys work it out quickly? So just draw the small signal model for this and work it out, right? Small signal, this is ground. So if I increment the voltage delta V, please work out and tell me what delta V naught is. Okay, so if you guys got it, it's good. Else you can work it out. But see, recording. See, even intuitively, right? So what we have here is this structure, right? Voltage is applied here, and we are trying to get the output here, right? Yeah. So very roughly speaking, it's not really correct, but roughly speaking, it's like a voltage divider, right? So if I call these R1 and R2, for a resistor divider, what is this ratio? R2 by R1 plus R2, right? And I mean, again, if you think about it, R2 is basically the resistance you look from the output to ground. The sum R1 plus R2 is the total resistance you look from the input to ground. Okay. So if you go by that logic, what is the resistance you look from the input here to the ground? L2M to M4. That's basically roughly GM4 R04 times R02, right? This is the looking from the input to ground. That's what is coming at the denominator. Now what about the resistance at the numerator? That is the resistance you see from the output, right? So this is R02. So this is what it's going to be, right? Okay, this all, I mean, good approximation. So delta V by, okay. So this again proves our intuition, right? So we expected that if you change this voltage, this should change by a smaller amount because you have a current buffer here, and that's what happens here. Okay. Cool. So let's get back to where we were in the last class. So we basically tried to use this cascode and increase the output resistance. So we had the PMOS current source, PMOS cascode, NMOS cascode, and the NMOS GM, and you had a copy here. Okay, so let me label these guys. Okay, and this is where we applied the input, we took the output, and then we saw how to generate this voltage, and for that we connected these two guys together. Okay, and these are bias voltages. I'll call VB4 and VB6. So here what was the short circuit GM we had? GM1. And what about the output resistance? I mean, we did the calculation. Finally, it turned out to be the cascode, cascode impedance looking down in parallel to the cascode impedance looking up. So that was this R4, R02, R06, R08, right? And we also looked at the slew rate for this. And what was the slew rate? If I had a capacitance CL at the output, slew rate was also I naught by CL. Okay. So now let's look at the common mode ranges at the input and output. So that's what we started in the last class. Oops. Just a second. Okay, so for oops, I didn't wash this happened here. Copy this once. Okay, great. So first let's find the common mode range you can have at the input. So for this, we'll assume that the input is basically raised together. So let's say this is Vi. So first let's see what happens at the lower end. If you keep reducing Vi, So we have I naught also realized by current source. So if I keep reducing Vi, the source voltage here drops down, and finally you will be limited by the minimum drain to source voltage for this transistor. So what is the minimum Vi you will have to maintain? No, Vi is the input here, right? It's basically we need some gate to source voltage across M1, M2 plus the drain to source voltage minimum. So it's basically VGS of M2 or M1 plus the minimum drain to source voltage of M0, which was the overdrive voltage of 0, and each of these is at I naught by 2. Okay, I'll not write it, but I'll say. Okay, great. So now let us say I keep increasing Vi. Which of these transistors will start to enter triode region? M1 and M2 at least makes sense. I am just changing the gate voltage of this, so better, this guys only be affected by that. And if I call this drain voltage as VD2, what is the maximum Vi can go? If the drain voltage is VD2 plus 1 threshold, right? And how is VD2 fixed in this circuit? No, I'm asking in the circuit, how is the operating point of VD2 determined? VB4? Yeah, in the last class we just looked at it. You see that we have a current I naught by 2 in both the branches. So which means you need to maintain a particular gate to source voltage across these guys. So if the gate is at a voltage VB4, what will be this voltage VD2? VB4 minus a gate to source drop, so that is VGS4 at a current I naught by 2. Okay, and please remember VB4 itself is a bias voltage that is under your control. So this also will have a range of voltages. Okay, so VB4 itself will have its own range, so that all of the transistors will remain in saturation, right? So let me write it finally. So maximum Vi you will have at the upper side, it is VB4 minus VGS4 at a current I naught by 2 plus a threshold voltage. At the lower end, it is determined by this guy. So let me write explicitly. Fine. So this is the range of the input common mode you can have. Great. Oh yeah, thanks, thank you. Yes, correct. You're right. Thanks. Yeah. So M0 carries a current of I naught, right? So this has to be V overdrive at a current I naught. Thanks. So you'll have to be careful here. So this is at I naught by 2, where this is at I naught. Okay. Cool. So now let's look at the output side. Okay, nice. So again I'll replace this with. Okay. So here let's find what is the range of output voltages the opamp can accommodate. So first let's look at the lower end. So if Vout keeps reducing, again which of the transistors will get affected first? M4. So what is the minimum Vout we can have? The gate voltage minus a threshold. Gate voltage is VB4 minus the threshold of this guy. Done. Again VB4 has its own range. Okay, it's not like fixed voltage. You can have a range of voltages for VB4. Now let's do the other end. So if I keep increasing Vout, which is getting affected? M6, the PMOS. So what is the maximum Vout can go without causing M6 to enter triode region? It's gate voltage plus the threshold. Fine. So gate voltage is VB6 plus, I'll just say mod VTH of 6. Fine. So again, this guy will have its own range. Okay. Cool. So let me copy paste the input range once. And by the way, just one fine point. So here the ranges we compute, if you see how we are doing for the input, at the input we are assuming both the inputs are increased or decreasing together, right? So it is the common mode for the input. Okay. So this is the common mode or the common signal that you can apply to the inputs, making sure all of them are in saturation. Okay. The output here is basically there is no common mode or nothing, right? It is the total output. So this output is, this range you compute is the absolute minimum and maximum for the output that the op-amp can tolerate. This will include, you know, all your small signal, large signal, everything. This is the absolute minimum and absolute maximum at the output. Okay, it's one difference. So let me copy paste this guy. I copied, fine, I made a mistake. So this is now the range for the input common mode, and this is for the output side. So now let us say I try to put this guy in unity feedback like this. Okay. So this is Vi, and ideally this will also be at Vi. So here output is forced to be at Vi. Okay. So now as we saw in the last class, input seems to have its own range, output seems to have its own range. So here we are forcing input to be output. So what is the minimum output we can have now? Yeah, that will be the maximum of the two minima. So let's look at the minimas here. This is 1 and this is second. Now which of these two do you think will be higher? I mean, just your plain intuition. Huh? This will be higher, is it? Okay. Okay, let me ask you this question. At least not going into detailed calculation, but say if you go up, right, from here to here, do you think the voltages will increase or decrease? At least logically makes sense, it will keep increasing. So do you think VB4 will be greater than this or less than this? Most likely it will be greater than, but of course need not always be the case, but most likely it will be greater. Make sense? Yes. So now can you say what will be higher? This, I mean, this if you can actually work out the ranges for VB4 and find out, but you will find out that this guy will be the maximum. Okay, this will be the higher among the two. So the minimum output you can have when you put it in a unity feedback like this, VB4 minus VTH4. Okay. Again, I'm giving a qualitative reasoning, but if you want, you can actually work out the ranges for VB4 and actually convince yourself. Okay, so that sets one limit. What is the maximum? Maximum will be the minimum of these two. So let me circle these. Oops. Okay, now again by the same logic, which of these do you think will be lower? At least VB6 will be higher, right? So VB4 will be lower. Okay, so here the maximum will be limited by this guy. So this is VB4 minus VGS4 at a current I0 by 2. Okay. So this is the range we have. So what is the total output swings we can have? By output swing I mean the difference between these two, maximum and minimum. So that will be basically what, VTH4, right? What do we have here? What do we get? VTH2 plus VTH4 minus VGS4 at I naught by 2. That's the difference between the two, right? So if this basically is VTH2 minus, okay, so now you can see this basically one threshold voltage minus an overdrive voltage. Okay, so I mean now let's say you have supply of 0 to say I don't know 1.8 volts, so threshold voltage will roughly be around 0.4 0.5, okay, and overdrive can be as low as say 100 millivolt, let's say 50 millivolt also we can go. You see that if you put it in a unity feedback, the range you can have for the output is very limited. That's the point I'm getting at. Okay, so oh, by the way, I forgot to tell you some names. So anytime you come up with a new circuit, you have to name it, and this is called telescopic cascode, because some guy thought it looks like a telescope and he decided to call it, so everyone is calling that. Okay, I mean the idea is looking up also you have a cascode, looking down also you have a cascode, it looks like a long telescope or whatever. Okay, so let's get back to this. So the problem with this telescopic cascode is that it as you see it provides a very high gain, right? But the issue is it has a limited output swing when you put it in unity feedback. Okay, this is one drawback. Great. So now we saw a case where we are trying to connect the output and the input like this, but not all applications will be doing this, right? So let us say we don't constrain ourselves by making input to be equal to output. Okay, so let's see what is the absolute maximum and minimum you can have for the output. Okay, so let me copy this once. And we already computed that, here it is. So even in this we'll find what is the absolute maximum and minimum we can have, right? Because as I mentioned, VB4 and VB6 also has its own range. We'll try to find the absolute maximum and minimum. Okay, so let's say I try to find the maximum. So here I find V out max is, what is the maximum? It's VB6. So since I'm looking at maximum, that is maximum of VB6. You get 6. So now can you actually work out and tell me what is the maximum you can have for VB6? Please work out and tell me what happens. What is it? V overdrive of M6. Why is M4 getting affected? VB6 is here, right? So if I keep increasing VB6, no, you are maintaining a fixed current. See, this guy is a current source.
That's so. VS will increase.
Exactly, right. So what has a problem now?
That has saturation problem.
M8, right? So if you keep increasing VB6, like he pointed out, the transistor M6 is biased at a current of I0 by 2. So to maintain this current, the source voltage here will also increase. So the source voltage of M6 is the drain of M8. So M8 will limit it. And what is that voltage now? Can you tell me? What is VB6 max? Can someone work out and tell me? G6. That's not right. VGS, I mean, it's not right actually. Okay, what are you saying? VDD minus? Six. This is 8, you're saying. Okay, this side got one answer. Any other answer? Okay, so what is VD8? The drain voltage of, I mean, the voltage at this node. How is it fixed by again? No. I mean, in this circuit, what fixes the operating point voltage of VD8? Huh? No. What is that voltage, operating point voltage? Huh?
VGS6 and VB6 will be
No, I mean, that doesn't fix it, right? I mean, what is it that
VSG6 will fix it because I naught by 2
right? So again, current flowing here is I naught by 2. See, please remember in MOSFET, the current dependency is only most like, I mean, you want the MOSFET to be dependent only on the gate to source voltage. Okay, so drain voltage doesn't get fixed automatically. As we'll see later, we need to have some mechanism later, or we should have a configuration like this where some gate to source voltage is fixing a drain voltage. So here VD8 is fixed by, so what is VD8? Can you tell me in terms of the gate voltage? If the gate is at VB6, what will be the source voltage?
VB6 plus
Mod VSG6 when it's carrying a current of, I mean, I don't have to write mod VSG6, it's just I naught by 2, right? So now tell me what is VB6 max then? And what is the maximum value VD8 can have? It's limited by this guy.
VD minus VD8 should be equal to gain over
Okay, so VD8, what is the maximum it can have? It depends on the gate voltage here. And what is the gate voltage? This is supply. We have a source to gate drop here. The gate voltage is VDD minus VSG of 7 or 8. That is this gate voltage. The drain here can go one threshold higher. Fine? That's fine. So which means my VB6 max is, if I call everything as max, maximum of VD8 minus source to gate, right? So that's VDD minus VSG8 plus mod VTH8 6. Okay. So this is basically, I can rewrite it like this: overdrive of 8 is the 6. Fine. If there is some confusion, please let me know. I'll clarify it once. Okay, so if this is fine, I mean, now we have found the maximum of VB6 max. So what is V out max? It's this guy VDD minus overdrive of 8 minus source to gate of 6 plus mod VT at 6, right? This is from here. So how can I simplify this? So this is basically minus overdrive of 6, okay? Right? So here, let me write it here. V out max is VDD minus overdrive of 8 minus overdrive of 6, and you can see this is the minimum drain to source voltage we need to maintain, and so it's the VDD minus the minimum source to drain voltage, which is one overdrive of M8 minus one more source to drain voltage for M6, which is overdrive of 6. Okay, great. So a couple of fine points I want to make. Okay. So if you recollect, the way we came to the circuit was this: we started from this, and then we told we'll try to generate this gate voltage, and that we wanted to do as follows. We told we'll try to make sure the current flowing through the NMOS branch I0 by 2 will be forced in this PMOS branch. So the current from M7 is buffered by M5. So we decided to compare the current here with the current in the NMOS, and that's why we made this. Okay. So I was surprised no one asked the question. So why can't I mean, is there some other way in which I can generate this voltage? Or is there some other current that I can use to compare with I0 by 2 here? So in this circuit I compared the current in this transistor M5. So what is the other current I can compare here to enforce the PMOS current to be I0 by 2? Huh? Sorry? No, M2, no. M6. Oh, I mean, that is the same thing, right? I mean, you look from left or right, that's okay. M7 is also fine, right? I could as well have compared this current. I mean, again, the same logic. So, this current will be I0 by 2, so I can basically do this also. Right? It shouldn't be surprising because when we had the 5 transistor OTA, we just had this. Right? And you can think that I'm adding a current buffer after that. Now, by the same token, how can I generate VB6, this voltage? I can do a connection like this. Is that fine? So on paper, this is also fine because looking in here, we still have the cascodes, right? A PMOS cascode and NMOS cascode. Thus the difference is the way in which we have generated the bias voltage. Okay, so in this, can you tell me what will be the maximum possible value for the output? So this is the circuit we have. So here, what is V out max? So that will be limited by which transistor now? Huh? M5 has no issues, right? Its gate and drain is connected. This is M5, its gate and drain is connected, no issues. So if V out goes higher and higher, what transistor will start to cry? see, simple logic. I mean, this drain is increasing. Transistors connected to that node is what is this issue. Now I have M4 and M6. If Vout increases, will M4 be happy or not happy?
Be happy.
Right? So what is what will create issues now? Other transistor is M6, right? So what is the maximum Vout can go then? If I call, let's say this is gate 6, VG6. I mean, it's not a complicated question. So I'm just saying we have a PMOS transistor, gate voltage is at VG6. What is the maximum drain voltage for the PMOS transistor? One threshold higher than its gate. Okay, so this is VG6. And what is VG6? What is fixing VG6? Yeah, so if you think about it, we have a source to gate drop here, right? So this is, if I call this as VG8, what is VG8? It's basically the supply minus the source to gate voltage. So that's what is here, right? So this is VDD minus source to gate of M8. So this is the voltage applied to source of M5. So what will be the voltage at a gate of M5 or M6? This voltage minus one more source to gate voltage. Is that fine? So this will be VDD minus, what is it? VSG8, which is this voltage at the source, minus one more source to gate voltage. Okay, plus mod VTH6. Fine. So please simplify this for me quickly. How can I simplify it? Oopsie. So this is VDD minus, how can I simplify it? In terms of the overdrives. I mean, this is basically overdrive of M6. So if I write it as overdrive of M8, what is the term I should add or subtract? Should I add or subtract? I should subtract. Okay. Just a simple manipulation, right? So now you compare these two, see which of these has higher swing. Left or right? Left one. Okay. So left one is the maximum it can go is VDD minus overdrive voltage of two transistors. But when we do this connection as we have done in the right side, it is VDD minus two overdrives and it is lower by one more threshold voltage. Okay. So although the gain you will have here is same, the swings will be even limited in this case. Okay. And for this reason, this configuration, which I am showing in blue, is also called high swing cascode. Okay. Because this is also another cascode, what we have in the right, but the swings here are much limited. Is limited. That's all. Any question? Okay. So okay, now we have this guy. So here everything is fine. We still have to generate these voltages, right? Now, as we saw earlier, these voltages have their own ranges, and let us say I want to fix these voltages so that output can go maximum and minimum. Okay, and by the way, here we have found the maximum output. We found the maximum output like this, right? Oops. VDD minus 2 overdrive what do you think will be the minimum output? Okay, I can go again here. So in this, the maximum output we had was VDD minus the overdrive of M8 and overdrive of M6. What is the minimum do you think it will be? We need to have minimum overdrive for M0, right? And you need to have a minimum overdrive for M2. See, basically the output at the lower side is drain to source voltage of M4, drain to source voltage of M2 and M0. Okay. So here it's going to be overdrive of M4, overdrive of M2, M0. Okay. So you need to be careful only when you have some kind of diode connections like this, right? So otherwise, if the gates are all floating, I mean free to be at any voltage, you can directly do this. Okay. And yeah, when you do this, please be careful, because when I'm writing it, I'm doing here it because the gates are all controllable independently. It is not fixed by something else. For example, in this circuit here, it might seem like again the maximum you can have is VDD minus overdrive of this minus overdrive of this. But that's not the case we have, right? You see that we have additional VTH. So the moment you have a diode connection like this, please be careful and work it out. Okay? But if the gates are all free to be biased at any voltage, then you can directly do this. Okay. So, okay, just a quick exercise then. So, let's say when we had this 5 transistor op amp, so here can you tell me what will be the maximum output? If I label this M1, I mean based on what we did now, can you guess what this maximum value will be and minimum value will be?
VDD minus
overdrive of 4. Okay. I mean here again you work out, I mean since you have the diode connections, you work it out, but you'll find that this is basically this. And similarly, what will be the minimum? Overdrive of 2 plus the overdrive of M0. And again when you write this, you should be explicit, because M4 is biased at I0 by 2, this is at I0 by 2, whereas this is at I0. Okay. So I mean when you are writing in exam or whatever, just overdrive doesn't make any sense. You should also say what current it is biased at. Similarly, when you write gate to source voltage, source to gate voltage, you should also mention what is the current, right? Okay, so last thing. Okay, so now here we know everything. So we know how to, I mean everything is now at a transistor level. The only thing pending is generation of the two other voltages, VB4 and VB6, right? And again they will have their own ranges for proper operation. And let us say I want to choose these two voltages so that my Vout will be at its maximum swing of VDD minus overdrive 8 minus overdrive 6, and at minimum side it will have whatever it is. Okay, so let's see how we can generate quickly. So if I were to have this maximum Vout, we already computed what should be VB6. So let me reuse it quickly. Where was that? So I already found what is the maximum VB6 I need to have, right? If I have this VB6 here, then my output will be maximum and equal to the value we have. Is that fine? So let's see how we can generate this quickly. VB6 max is VDD minus V overdrive 8 minus VSG6, all at a current of I0 by 2. I'm not writing it for the sake of simplicity. So now I have to generate some bias voltage, which is this, right? V overdrive of one transistor minus source to gate of another transistor. So any starters? It's okay to say, right? Someone was saying something. Huh? See, the question is, we saw that if you want to have this maximum output swing, the bias voltage VB6 must be at this voltage. The question is, can you come up with a circuit that will generate this? I mean, of course, one thing is you sit and calculate what this guy is and put a voltage source there, but it's not the practical solution, right? So how do you suggest? What should I do? Assume that you have currents I0 and I0 by 2. That's the only thing you have. Yeah, you suggested diode connection. How do you?
Like two cascode and they will be diode connected.
So you're saying like this? And what should I connect here? What currents I should have here?
I0 by 2.
I0 by 2. Okay, so he's suggesting this. So let's say what we get here. So let us say I have M8 here and M6 here, right? What will be the gate voltage here? If this is VDD? VSG8. So what will be this voltage? VDD minus VSG8. But that's not what we want, right? But it's close enough, right? I mean, we wanted to generate VDD minus VSG6 minus overdrive 8. So let's expand it. VDD, overdrive is basically VSG8.
Resistor can be connected. So with the resistor value we can see that it is dropping on the.
So where should I put the resistor?
Above I0 by 2.
Here?
Yeah.
Okay, so if I put a resistor here.
And the drop across I0 by 2 R we can assume.
No, this voltage is this fellow. This will be higher or lower than that? Lower than that. You want a voltage that is higher than this voltage by a threshold. If you direct current a normal MOSFET, again we'll have a gate to source drop, right? But we want it to be equal to a threshold voltage.
You can connect Zener diode in
Xeno diodes are all nice in textbooks, man, but in ICs we don't have Xeno diodes, okay? I mean, okay, he actually had a good starting point, right? You want to have an additional voltage drop somewhere. So he's suggesting we can put a resistor here, but obviously putting a resistor like this is not going to work. Okay, so but this is a good starting point. So let us say we have this. Now right now we have connected it like this. Okay, so this is basically this voltage. Sorry, just a second. PSG8. I want to generate a voltage which is higher or lower than this. Higher. So in the stack I should go at least somewhere higher, right? So obviously I can't go here. So but can I do something here? So now if you put a resistor here, I know the gate voltage, which is basically this voltage. This is the gate, right? This is this. So the voltage at the other end of the resistor will be what? VSG8 minus VSG6 plus I0 by 2 times R. This is a decent solution, but again we need to make sure the resistor I naught by 2 I naught by 2 times R must track a threshold voltage. Okay, so this we cannot enforce all the time, but it is would work. So can you suggest something else that will generate a threshold voltage or close enough to a threshold voltage? Forward bias diode. No. This is not. See, this is threshold voltage for a MOS transistor, right? So can you think of some way in which you can generate a voltage which is close enough to a threshold of a transistor? So if I do this, I'll do with an NMOS first so that it's easy. So this is what is this voltage? It's a gate to source voltage. So what is a gate to source voltage? What is the expression for this? Just a second. Yeah, what is the expression for this? In terms of the current, mobility, etc. What is it? Root 2 some I by something plus. So can you think of a way in which I can make this approximately equal to VTH? I equal to 0, yeah, that's it. Some other practical, not a mathematical solution, a practical solution. So if you basically here, if you tend W by L to infinity, not infinity are very large, right? Then gate to source is approximately a threshold. Okay, so we can do something similar here with the PMOS also. So let me quickly copy paste this. So here I need to have another PMOS transistor which is diode connected like this, but this guy must have a very large W by L. Okay, so I'll remove these guys. Okay, so then its gate to source voltage will be approximately a threshold voltage. So now if I tap this voltage, this will be the gate voltage, which is VDD SG8 minus VSG6 plus a mod VTH. Approximately this. That's good enough. Okay. So now we can take this guy and basically do and make a connection like this. Okay. Now similarly you can, sorry.
These 8 and that 8, both are different transistors, right?
Everything is a PMOS, right?
The M8 over here and that M8 over.
Oh, okay. Yeah, sorry. Yeah, I meant, yeah. Basically, you should have a replica of M8. I'll call M8 prime, M6 prime. Okay. I mean, you want this to have the same source to gate or overdrive voltage as this guy. So this should be copy of M8, right? Because you want to generate VDD minus VSG of M8. So you better have the same identity.
You just apply VV6 like calculated VV6 then doing this big.
It turns out all the calculations you do on paper will not work on ICs, because first of all, as we'll see later, the square law equation first of all is not valid. That's just an approximate expression. Second of all, even if it were valid, you might calculate something for mu and COX and stuff, but on ICs and big wafers, this will have a lot of variation. So we look at it later. It's called process variation. So a single value calculate will not work. Plus, it will vary with temperature also and stuff. So on exams, yeah, you can find the nice round values and put it, but doesn't work in practice. So we'll have to have some tracking circuits like this that will generate the required voltages. Now similarly, you can do some similar stuff to generate VB4 also, right? And that's how you'll bias it. Okay. And now if you see, I mean, if I just show the circuit, it looks quite complicated. right? But I mean, if you understand how each of these come, then it will make sense to you. Okay. So, I mean, this is not obviously the only way in which you can generate this voltage. There are of course multiple ways. So I probably show one last way in which you can do, or one other way in which you can do. So you need a voltage which is VDD overdrive 8, sorry, or just a mod VTH, right? And again, what is VSG8? If you assume square law operation, it's going to be square root of some 2I naught or some 2I. This is mu PCOX of the transistor M8. Okay, plus mod VTH of M8. I think this was M8 or M6, I forgot. So let's say this is mod VTH8. Okay, so this is what VDD minus one threshold goes off. So you'll have square root of 2I by mu p COX times some W by L. Okay, so I'll have plus one threshold voltage of 6. So now can you look at this expression and tell me some other way to generate this voltage? Huh? Minus, is it? Okay, yeah, okay, fine, yeah, or I'll just do this, fine, yeah. So now you look at this expression and tell me some other way in which you can generate it.
Single diode-connected MOSFET with that particular W by L.
Right? I mean, this is same square root of 2I by mu COX. The W by L must be this guy. So again, this is all rough calculation. So if you calculate this and use a PMOS transistor, with this, W by L prime I'll call, then its gate to source voltage, I mean this voltage will be approximately the voltage U. Okay. This of course one other way in which you can do. Okay, so let's stop here and we'll see tomorrow on next class on Tuesday.